So my presentation will be divided into 4 parts, which will present what Peter just briefly announced. First, I will show you the improvement of a constitutive behavior law called Polyamide, due to it was developed during the first project piloted by France Energy Marine about polyamide 6 mooring line. So it's the Polyamide law, and he worked at validating it during this project. Then I will present you the long-term creep study, the fatigue study on polyamide 6, and briefly the development of a 3D meso-scale model. So to start, the Polyamide constitutive law, it's a constitutive law that aims at representing the complex viscoelastoplastic behavior of polyamide 6 mooring lines. It has already been implemented into one logiciel for simulating on deep lines. So we can use this law to represent polyamide 6 line, for example, for the design of buoy. So here is a picture. So it's a constitutive law that has 3 main parts, and it contains 11 parameters. So the first part here aims at representing the instantaneous elastic response of the line. Then there is a part that describes the time-independent response of the mooring line. So it will be plasticity and strain due to the constriction of the rope, and a delayed elasticity. And then here is a part that aims at describing the dependent response, which is the viscous response of polyamide 6, which is one of the more hard aspects to represent with those type of law. So it was developed during the Polyamide project, and it was identified on a 4-ton scale polyamide subrope. So it's a laboratory scale. And the aim during this project was to identify it on a higher scale subrope with a more realistic construction, so a 7-ton subrope, to validate it on other type of test sequences than the one used for identifying it, and maybe to improve some parts if needed, some of the here functions that describe each of these blocks. So to identify this law, we have to perform a multi-relaxation test. So it's a test that lasts one day maximum, and it's called multi-relaxation because we perform several relaxation plateaux. So here on the right, you have the experimental protocol. It's a strain control test. So we perform the strain plateau, and it lasts 1 day. So when it was developed, using a servo test machine. So it's a machine to test laboratory scale subropes. And so during this project, we could implement this procedure on a more realistic test machine. So it's a test bench available at Ifremer to test on a higher scale subrope. And so we could perform this test to identify the 11 parameters for a 7-ton subrope scale. So just a reminder, this was the identification on a 4-ton Vigian subrope during the Polyamide law. So here are the different functions of the different blocks of the Polyamide law, and this was the result when identifying it on a 4-ton subrope scale. So it was shown during this first project that it was well describing the polyamide 4-ton subrope scale, with a good description of the relaxation, and here it was first validated on another type of sequences, so a multi-creep test, and it was shown that the shape of the cycle was well represented, even if we have a slight offset between the 2 curves. During this project, we just proposed a modification of the viscous part, so we changed this expression. It's not the same one as in the Polyamide project. It allows us an easier identification of the parameter and for the viscous part. So here is the result after the identification on the 7-ton subgroup scale. So again, you have here the logarithmic strain versus the time. Here it's the strain that is plotted, and here we have the same experiment for specific stress. In blue, it's the simulation when using the Polyamide law and the identified parameter, and in red, it's the experimental results. So we can see that the law is adapted to describe more realistic construction. We have a good description as well of the creep part. And here for the specific stress, we can see we have a good description of the relaxation, and we just observe a difference between the curve when we get to higher specific stress. But it's a good description. And so we tried to validate it on a more realistic test, which is called a stochastic test, using a database of an experimental test performed at Ifremer on 7-ton subgroup sample. It had a complex history of loading because it was tested several times. So to try to represent this complex loading, we performed a simulation, which is a simple simulation, but we put the maximum load at 40 kilonewton here to try to represent the higher loading the subgroup had seen before being submitted to stochastic loading. And then we performed this simulation. And so here is the confrontation of this simulation with the experimental data we had. So in orange, it's the simulation, and in blue, it's the experimental result. Here we have the strain plotted versus time, and here is the stress versus strain. So what we can see is that here on your right, we have the dynamic module versus time. And what we can see is that the simulation has a good prediction of the dynamic stiffness during the test, but we have some creep that happens during the simulation that we are not seeing in the experimental results. And that is because of the complex history of loading the subgroup had seen. And so we tried to change a bit the simulation with a different history of loading to see if we could get a closer prediction. And so here you can see that this time, when changing the history of loading before the stochastic sequence, the simulation is well predicting the experimental result with less creep, and again the dynamic stiffness is well represented by the law. So now I will present you the long-term creep study. So as Peter said, we used a test bench that was developed during the Polyamide project. So it's a test bench dedicated to do creep tests on the 4-ton subgroup. So it's the laboratory scale. We can do 3 tests at the same time on this test bench. So here you have plotted the logarithmic strain versus time. And you see we have 3 tests that have been performed and investigated. So those data are precious. As you can see, the creep and recovery test lasted more than 2 years, so 800 days. So those are very precious data. And we have tested 3 different loadings. So 1 creep at 25% of the MBL of the subgroup, 1 creep at 39% of MBL, and another one at 45% of MBL. And if we focus on this creep part, here you have plotted the logarithmic strain versus creep time in log scale. So the solid line are the result of those long-term creep tests. And here the dashed line are the same as our other creep tests, but short-term creep lasting only 3 hours. And this show that the polyamides show a logarithmic linear behavior for creep, and we can use a simple logarithmic fit to predict a long-term creep of 2 years using only, for example, here a 3 hours test of creep. And the speed, the kinetics of the creep are not critical at all for the mooring application. So this study helps validating the use of polyamide seeds for mooring lines without critical creep behavior. Then we extend those tests. So one of the tests that was in recovery, we reloaded it. And one creep test lasted more than 3 years. So the red curve here is a creep test lasting 3 years. So for this test, we can see that we still have no increase of the strain. So for now, the behavior is still stable. And the reloading, I will show you just after, showed us that we had a slower creep kinetic. So I will show it just after. Yeah, just here. So for the second reloading, we have we could see that we have a slower creep rate. So the history of loading will impact the creep kinetics, but not increase them. So it's okay for the application. And then here we have plotted the specific stress versus logarithmic strain. The yellow line is for the first creep loading, and the blue line is the second one. And then I propose a shift for you to see that during the second loading, we can see that we have a subgroup that is a bit more stiff, a bit less than 2 times more stiff. And an investigation that we performed showed us that it was mainly due to the constriction at the strength scale of the subgroup. And we performed the last another test, another cyclic creep test during long times. And this cyclic creep test aimed at evaluating if a creep during a short period, so here is a peak creep during only 1 hour at a higher load, would generate more creep strain than a long creep, at a service tension. And so what we could show is that the short-term creep during the storm will produce more creep than the long-term creep strain, strain at in-service tension. And so that we should design our platform using the storm conditions. And that were our main conclusion on this test. Finally, we tried to confront the Polyamide law with long-term creep test. And so here you have in red an experimental result, and in black the simulation. And what we could see is that the law is still not adapted to describe long-term creep. It stabilizes too fast. And that's why a next project proposed by France Énergie Marine, the BAMOS project, will try to improve this part to be able to describe long-term creep using the Polyamide law. So now I will present you the fatigue study we performed. So we performed the fatigue campaign on, again, a laboratory scale subgroup, so photon scale subgroup, at a frequency of 0.1 Hertz, which is a frequency comparable to the swell frequency. And our fatigue campaign was performed between 2% of the MBL and the varying force maximal. So we were cycling the subgroup between the 2% of MBL, then a maximum force. And so the load ratio was close to 0 for all of our fatigue test campaign. We had to perform the test at least in wet condition, because water will play the role of lubricant between the scale. So we first immersed our subgroup at least 24 hours before each test for it to be saturated in water, and then we maintained the rope wet during the test using a vertical watering system, and then we perform our fatigue test to failure. So we obtained the curve, which is represented by the blue point here. So we could reach 10⁵ cycle to failure for 25% of MBL of maximum load. So we could show that for now, the fatigue life of a polyamide cyst on photon scale subgroup is still following a log linear evolution, so we don't have a decrease of the fatigue lifetime for lower load ranges. And we compared those results to more realistic construction, because the photon construction is a laboratory one. And we could show that the photon construction is enough to well describe the fatigue lifetime, so to give a good order of fatigue life. And it's conservative because it will a bit reduce the fatigue lifetime. As you can see, the fatigue curve is shifted to the left because of the specific construction used to test it on a laboratory equipment. Again, we tried to confront the Polyamide law to fatigue test. So here you have the specific stress versus the logarithmic strain. In blue, it's the fatigue test. So we can't see really the cycle because we have an evolution of the cycle. So you can see it on the right. The curve for the experimental results are represented by the circle, and the curve predicted by the law are represented by the cross line, the cross. And what we can see is that the Polyamide law is well describing the first cycle with a good hysteresis, good stiffness, but it will not represent the change in properties during the fatigue test on the photon subgroup scale, which was mainly due to the construction. And so again, the next project of France Energy Marine will more deeply investigate the behavior of polyamide during fatigue test by performing test with strain monitoring to validate this result, and again to try to improve the Polyamide law, maybe to describe more accurately the evolution of the shape of the cycle. Finally, we performed tomography analysis to evaluate the degradation of our photon subgroup sample after a fatigue test. So here is a sample after a failure in the eye of the splice at around 80% of its estimated lifetime, and we compared it to a virgin sample. We performed those tomography using this experimental setup, and here you can see the tomography results. So we have the subrope, which is composed of 3 strands, and the strands are composed of rope yarns. Here is for the virgin materials, and on the right it's for the materials after the fatigue test. And what we can observe is that after a fatigue test, the rope yarns that are constituting the strand are more dense. They are more compacted, and we also can see the area of contact between the strand. And those evolutions are due, in fact, to the radial compression that will be under which will be submitted those rope yarn in the center of the subrope. And so, if we look at the rope yarn, at the material, so the fiber constituting the rope yarns, we perform the microscope. We perform electronic microscopy images. So on the right is for the post-fatigue sample, and on the left for the virgin. And we could show that this change of optical shape we observe on tomography is only due to the organization of the material that is more compacted and the fiber are more aligned. Finally, if we propose a zoom, we can see a mark which is due to the friction between the fiber during the fatigue test. So that shows that we have an evolution of the surface, the friction coefficient between the surface and contact, because we have a degradation of the material, and we have a change in shape of the fiber. Sorry, and so this is important to notice. So finally, a study that we did during the MONAMOOR test is the study of the self-heating method. So it's a method that aims at predicting the fatigue lifetime quickly. So it's it's an experimental test that lasts 1 day. So we perform the cyclic test on our sample, And again, it's between a fixed minima, and we change the maxima between each block. And this test lasts only 1 day. The specificity is that we will monitor the temperature of the sample during the test. So here we have an infrared images of a subgroup weight, and so the infrared measurement we perform. And we can calculate a global dissipation per cycle. And so we can plot the global dissipation per cycle versus the maximum load between each block. And this allows us to link mechanisms that will induce energy conversion to the mechanism that induce the damage and then failure scenario during fatigue test. And finally, with the use of an energy criteria based on this curve, we can propose a prediction of a fatigue Valor curve. So this is the first prediction with a graphical analysis. We could validate the repeatability of the protocol. We could show that with only one day test, we can predict the fatigue lifetime very quickly, which could allow us to do screening of construction and get the fatigue curve with only 1 day of a test. And so we still have work to perform on this analysis, this self-fitting method, to understand more the different dissipation mechanism of this curve, and to be able to propose a reliable prediction. And so I will just be quick here. We also developed a meso-scale model. So this model is based is a model that aims at understanding more the construction, the mechanic of the construction of the rope. So this time it's a 3D scale model. We represent each strand by cylinders in a finite element analysis logiciel. So we use Abacus, and then we implement a behavior law inside each integration point. And this behavior law has to describe the behavior of the rope yarns that are composing the string. So this is just the theory. And I will just show you the results. So using this law, we could perform the first cyclic test on subrope. So you can see here what we performed. And we could propose a first comparison with experimental data. So here we have the load versus strain. In blue, it's the experimental result, and in red, it's what we obtain with our model. So for now, it's an hyperelastic model, so it will not show any hysteresis, but we can see that it is well describing the stiffness at the beginning of the test, with the tension that will be the tension in service for mooring lines. And we still have to improve the model to be able to predict the stiffening we observe on the experimental data, but this model is has a great potential, and to better understand the parameter impact, the parameter of the construction and their impact on the subrope response. And so, yeah, I'm done.